Welcome to this lectures on algebraic geometry and commutative algebra. Today in this lecture I will do what is known as Zariski topology. I should be more precise and say Zariski K topology. And this is the topology. I will recall what the topology means, and we are going to, our notation is the following. So K is a fixed base field, and A is finite type K algebra. And in this setup, in the last lecture we have defined what is Vk of an ideal A, where A is ideal in A. And what is this? Let us recall quickly. This is all those points A in K power n. So when this A is a finite type K algebra, that means A is a quotient of polynomial ring in n variables. So that means there is a surjective map, surjective K algebra homomorphism from polynomial ring in n variables to K. This is surjective K algebra homomorphism. Initially we have defined this Vk of polynomials, and those are all those points in K power n such that the polynomial vanish there. So this is same thing as f of A is 0 for all polynomials f in A. That is what the definition was. And we have also said that, so that means we have defined a map from, actually let me recall that quickly. So we have defined the maps like this. First we defined this for Vk was defined for polynomials f1 to fm, where these polynomial f1 to fm were polynomials in n variable. And this was by definition all those A in K power n such that fj of A is 0 for all j 1 to m. But we have also identified this set, this is an identification we have given, with homomorphisms K algebras from the polynomial ring in n variables to the base field K. This also we have identified with all those maximal ideals M in the polynomial ring such that the residue field at this M this is isomorphic to K as K algebras. This isomorphism is as K algebras. And this set we have been calling it a K spectrum of the polynomial ring. So strictly speaking, when we write this Vk of A for ideal in this A, what you do is you if you want to look at the K spectrum of A, that is look at all those maximal ideals of A such that the residue field is isomorphic to K, and then you can identify this Vk of A is all those points. So this should be for all polynomials capital A where it goes to the small a. And then we have defined a map. So we are thinking this map, we again now more generally I have actually defined for L any field extension L over K field extension, where we have K is a base field and this L is arbitrary field, and in a due course we are going to mostly assume, we will assume L is algebraically closed. But when I start doing that, I will mention it. So today L is arbitrary field extension of the given field K. All right. So let me write. Let me first. We have defined this VL. This is a map from radical. So the notation I used was small r rad small r, not rad, sorry, this was small r I of the polynomial ring in n variables to what I called it affine AFF K algebraic sets in L power n. This set, this is the set, and this is a subset of the power set of L power n. And in the last lecture I gave examples to show that this map, every element, every subset may not be an affine algebraic set, and this map was any ideal or any ideal generated by A, which is, suppose it is generated by F1 to Fm. This is not, we have not yet proved this, I will prove it, that every ideal here is finitely generated. Assume that for the time being, and this ideal, where does it go? This go to VL of ideal A, which is by definition all those elements A in Ln such that Fj of A is 0 for all j from 1 to m. These are called affine algebraic K sets defined by the equation F1 to Fm. This is, let me write once at least, affine K algebraic sets in L power n defined by F1 to Fm. Now there are so many things that this depends on the these variables and coordinates, and these I am going to soon, after couple of lectures I will go completely coordinate free. It will completely depend on the rings, but just to understand the classical way what people were doing earlier and how it matches with the modern algebraic geometry, we have to do this. So this map, our main concern to discuss that when this VL map is bijective, that is our main concern. So I will just write that, just put a question mark, when is it bijective? That is what we are our main concern in couple of lectures. So that will give us a possibility to connect algebra with the geometry. That is what the main aim in this course is. Alright, now right now these affine algebraic sets are only, this algebraic description is there, but to bring in more geometry and topology I need to define topology on this. So let me recall now what is the topology. So recall that let X be a set, capital X be a set. So what is the topology on X? Then a topology on X is a subset of the power set of power set is, as you saw, it is denoted by Px, which satisfy the following properties. Number one, arbitrary union. So topology on X is a subset. Let me give a name tau. Tau is a subset of the power set and it satisfies some properties. And what are those properties? So tau is closed under arbitrary union. That means if I have subsets UIs, UI is indexed by arbitrary set I, if these UIs belong to tau, remember tau is a subset of the power set, so it contains some subsets, then union UI also belongs to tau. This is true for all I in I, then the union is also there. This means it is closed under arbitrary union. Second one, that second, tau is closed under finite intersection. That is, if Fi is not good, if Gi if I need some subset, so Vi, I don't want to use Vi. Script Fi is I is from 1 to n, Fi belong to tau for all I, then the intersection script Fi I is from 1 to n also belongs to tau. This means it is closed under finite intersections. Okay. Then third one, empty set belongs to tau and the whole set X also belongs to tau. If these conditions are satisfied, then we say that tau is a topology on the set X. And on the same set there can be many topologies. Let us see some quick examples. So quick examples. Number one, if I take the collection just two elements, phi and x. This is clearly a topology on, this is a topology on x. These are the only two elements, and this topology is also called indiscrete topology. So this is one. Second, these are two extreme examples. On the other side, if I take tau is the whole power set, this is a topology on x. This is called discrete topology. And this is called indiscrete. On x. So on every set there are definitely two topologies. Now let us take one more example on R. There is a topology called usual topology. This topology is used to study what is called real analysis. And what is that topology? In this topology, you describe what are the elements in this tau. So then, the usual topology on R is, I will just say, determined by the open, actually why Rn, R power n, by the open balls. What are the open balls? That is, usual notation is B, center is A, and the radius is R. And this is by definition all those x in Rn such that the distance from x and A is fixed A is less equal, strictly less than R, is Rn. So if I want to draw the picture, let us say in n equal to 2, the picture is n equal to 2. N equal to 2, that is R on R2. The open balls are, if I have to draw the pictures, they are this is the center A and this is the disk. Don't take the boundary. The boundary is omit from that and take only the inside thing. Only inside thing. This is an open disk. Disk because we are in R2. If you are in R3, then it will be like a ball without a boundary, only the inside of the ball. And what do I mean by determined? That means the elements of this tau are precisely unions of such disk. So this determined, this one will come soon. I will make it more clearer. Similarly, on complex numbers we can do it, and this one is usually used. This is the basis of actually real analysis, complex analysis, when we say open set, closed sets, etc. Okay, last thing, the elements of this tau are called open sets. Elements of tau, well, elements of tau are subsets of the given set X, that is the subsets of X which belong to tau are called open subsets. Actually, strictly I should write with respect to tau in X. because if somebody gives you a different tau, then the open sets are different. Okay. Now note that if I want to give a topology on a set X, I will give the complements. So the complements, so that is script F, this is all those y in tau, not in tau, all those complements x minus u, where u varies in this, is called the closed sets, the collection of closed subsets. So in other words, closed subsets are the complement of the open sets, and therefore open sets are complements of the closed sets. And what will be the corresponding properties of this tau, this F? Now the union will become, complement of the union will become intersection. So therefore intersection of those, so that means this F is closed. So the first property will become F is closed under arbitrary intersection. That will be the corresponding to 1, and second will become F is closed under finite union, and obviously third one, that empty set will become X, and X will become empty set. So these are elements in the F. So if you want to give a topology on a set, either you declare what are the open sets, but then they should satisfy the three properties, or you give a collection of closed sets, that is they should satisfy these three properties, and then we get a topology on the set X, where precisely the closed sets are the given ones, or precisely the open sets are the given ones. So now I want to give an example of a topology which is usually called as Zariski topology. So Zariski topology on L power n is precisely defined by so I will give you a collection of closed sets defined by taking closed sets as affine K algebraic sets. So what does that mean? That is F is taken V L of an ideal A, where A is an ideal in the polynomial ring, ideal, and we may assume it's a radical ideal, because we saw the zero set VL of A does not depend on the ideal A, but it depends only on the radical ideal. So these, now to show that they satisfy the properties of the closed sets, we have to check these four things, namely it is closed under arbitrary intersection, it is closed under finite union, and empty set and whole sets are elements there. So the first I will check third one. So what is empty set? Empty set is precisely VL of unit ideal or the polynomial 1, constant polynomial 1, there is no 0, that means it is empty set, or this is also same thing as VL of the ideal polynomial ring. This is a unit ideal in that polynomial ring, so it is this. This ideal is generated by the polynomial 1 or for that matter any other constant, non-zero constant A, where A is in K, A is a non-zero constant because they are all units. So empty set is there. How about the whole set? That means L power n. Okay, so L power n, I want to write this as 0 set of some ideal or some finitely many polynomials with coefficients in K, but well, that is VL of 0 polynomial or 0 ideal. So obviously ideal is 0, so it vanishes on every point. Already the only polynomial in that is 0, and 0 polynomial vanish on every element in L power n. So this is clear. So we have checked whole set and these are algebraic K sets. Now the first one, that is it is closed under arbitrary intersection. Closed under arbitrary intersection, what do we have to show? If I take a fine algebraic K sets, so they look like this: VL of AI, this is arbitrary family, I in I, and AIs are ideals in the polynomial ring Kx1 to xn, and then if you take the arbitrary intersection, that is this I from I in I, this is again, this should be again VL of somebody, because a fine algebraic K set is precisely VL of n some ideal. So what will that ideal be? The right candidate for that is summation I in I AI. Again recall that when I write this notation, this is the notation for the smallest ideal which contains all these given ideals AIs, or equivalently this is the ideal generated by all the elements in or any element in this ideal is precisely the finite combination of the elements from the corresponding AIs, and the coefficients allow them to be the arbitrary polynomials in Kx1 to xn. So we have to check this. Once we check this, our first condition will be checked. But note that these affine algebraic sets have the property that it is clear from this, the smaller the ideal, bigger the affine algebraic set. So what I am saying is, if A is contained in the ideal B, then VL of A and VL of B, what is the relation? That this is inclusion reverses. So therefore obviously all these ideals, some ideal contains all of them, therefore so this sum ideal AI I in I contains all the AIs, therefore when I apply V, this will be contained in all VLs. So that means this inclusion is clear, this is clear. Now to show that an element here is also an element here, that means what do you have to show? If you have a point here in L power n which vanishes on every polynomial and every ideal AI, then it also vanishes on this, but on every polynomial here, but any polynomial here is a finite combination of the polynomials with these corresponding AIs and the polynomial coefficients, but then each combination will also vanish. So therefore this is also clear. So this this was the property 1. So, we have checked 1, we have checked this was 3. So, we have checked 3. Now, we only have to check 2. And what was 2? 2 is it is closed under finite union. Alright. For that, what is enough to check is, so suppose this is I am checking second property. So, it is enough to check that intersection of two element, two VLA and intersection VLB, this also should be VL of somebody. That means it is union. Not intersection union. This is also VL of somebody, but what could that be? That is obviously you can guess that is intersection of two ideals, or this is also same thing as VL of the product ideal AB. And again here you use the earlier argument to check that is smaller the ideal, bigger the VL. So, I would just leave it for you to check these equalities, they are not difficult. You take an element here and show it is here, and note the fact that A times B is the smallest, A times B is the ideal generated by the products of the polynomials. So, with this you get a topology on L power n, and this topology is called a Zariski K topology, because we are defining our ideals are in the polynomial ring over K. So, now we are going to equip L power n with Zariski topology. And that is also one uses, if you see algebraic geometry books, they will use such a notation. This is affine, n dimensional affine algebraic affine space. This is affine n space over L. So, it is not merely a set, it is a topological space also. So, our map VL is now a map from the radical ideals in the polynomial ring to this topology, these closed sets. So, closed subsets in A n L with respect to Zariski topology. And now our problem is to study some basic properties of this topology. For example, this is what we will do it in next couple of lectures. So, what are the open sets? These are the closed sets. Closed sets we have defined the affine algebraic K sets. Open subsets of the Zariski topology are precisely now the complement. So, L power n complement VL of an ideal, radical ideal, but this I want to give some notation for this. So, this is dl of the ideal A. So, this is what all those points which is not here. That means there is at least one polynomial where it does not vanish. So, in particular let us take to understand, let us take ideal A. Suppose it was generated by a single polynomial, principal ideal. Then what is VL of A, VL of F? This is the 0 set of F. This is A in L power n such that F of A is 0. And what is D L of this principal ideal F, this is precisely all those elements A in Ln such that f of A is not 0. So, for example, it is interesting to understand this one. So, for example, let me just take f equal to say y axis. So, that is what. So, I am taking n equal to 2 and if you like L equal to K equal to L equal to K equal to R, so that we can draw picture. So, this, and I have taken this y axis and we want to know whether is it closed, it is open and so on. So, what is VL of, so when I say y axis, this means it is VL of x. When x is 0 you get precisely y axis. So, I should not write here f here. So, in this notation this is our f in the earlier notation. And what is the complement? dl of x, this is remove this y axis from the plane. So, this is you can write down in the notation, these are all those points a comma b in R2, and you are not allowed y axis, that means a can never be 0. So, a is non-zero. And we will deal with such examples more and more to get more and more acquaintance, and now we will also study little bit basic properties of this Zariski topology. Okay, we will continue after the break. Thank you.